All right. So, okay, yeah, so we're doing a little bit different from like the curriculum right now in the sense that we're doing section 44 and 45 together. The reason for that is that I think they're so related to each other, and if you guys go through it, you probably see that they're more or less kind of like encouraging each other, you know, like really the first section of 44 is more like introducing neural networks, the idea of, what's it called? Like a perceptron, you know, like a single perceptron network. And then section 45 tends to focus more on the deep learning aspect where we have multiple layers. And since they're so closely related, I kind of just combine it together that we can kind of more smoothly talk about it together. Because in general, when we're talking about neural networks, we're usually talking about deep learning in general, okay? And just kind of quick, like a thumbs up, you know, has everyone gone through by chance section 44 and 45? All right, awesome. So I see mostly thumbs up. And, you know, if you haven't gone quite through it, you know, maybe you just skim through it and stuff like that. That's okay too, you know. But if you have specific questions, definitely, you know, just interrupt me or, you know, say, oh, can you go into further detail about this or something? So kind of just initially, is there any initial questions you guys had just from reading those sections or just neural networks in general? No, see mostly head shakes and stuff. Oh, I see a little thing. Go ahead, unmute yourself, Jack.
Yeah. Hi. My question is, like, is the difference between a machine learning algorithm and a neural network is backpropagation?
Oh, that's an interesting one. I would say it's actually a little more general. Like, I would say the big difference. Okay, how do I say this? A machine learning algorithm, right? It's just basically saying that instead of you like classic, like, you know, programming where you have all the instructions put in place, and then it's like, if this happens, do this. If this happens, do this. Machine learning algorithms are meant to be like, all right, here are the hyperparameters, the parameters to learn off of. And you say, computer, you go ahead, figure it out from here's all of my input data, the data that is showing, what's it called? Like what you start off with, like your features and everything. And then here's the answers. And the machine learning algorithm is designed to try to figure out the best way to go from here, the inputs to the outputs. So in a lot of ways, neural networks are machine learning algorithms. And it's just a very specific type of machine learning algorithm, just like we talked about support vector machines. Linear regression is a machine learning algorithm in this way. There's a little more statistical learning than usually people kind of make that distinction. And we'll actually see neural networks look very similar to some other machine learning models, for example, will look similar to logistic regression, will look similar to support vector machines. So in a lot of ways, it's just different in a way that the way you implement it. So you mentioned about backpropagation. Backpropagation will be the way that we, how do I say this, is how we figure out the error and how we should adjust our machine, our neural network. And so you can think back in like support vector machines, for example. Support vector machines, that dial that we twist and stuff like that is the classification error, the margin error. Those are the parts that's going through. That's kind of the equivalent to for neural networks. Okay. Does that make sense?
Yeah.
Cool. Good question though. Yeah. So yeah, we'll get right into it then. And unless there's any other questions, and I'll share my screen. And it always takes me a second to share my screen. Okay. And of course, I lose you guys when I share. Sorry, everyone. Where did you guys go? I always put you guys on the side so I can see you guys nod or, you know, if you guys unmute and stuff like that. Okay. So there we go. Okay, so you guys should all see this table of contents, you know, about neural networks on top here. So again, this is in the repo that you guys can check out. All right, so let's go right into it, right? So I'm just running this little extra stuff so we can get some consistency, so we can run some code. But the first thing to talk about is like a neural network. So again, I kind of assume you guys have seen the section 44, 45 a little bit. So I'm not going to repeat, I'm not going to dwell too much on it, but I'll kind of add some extra parts. So the big thing about neural networks is the first thing you really should ask is saying, why do we do a neural network? Like, you know, Jack just mentioned, you know, we have other machine learning algorithms. So what makes a neural network different? And in a lot of ways, you don't always need a neural network. In fact, sometimes a neural network is the wrong like tool for the job. Not that it can't do the job. It's just that it's going to approach the problem differently, and it might take up more resources than like doing something like, I like to say, like a random forest. Random forest is a versatile, easy machine learning algorithm. that it's usually a great thing, like as an initial step. But neural networks really thrive when they're complex problems. So like when there's a complex problem that is really difficult to like get your hold on. So think things like that are very difficult, like image recognition. Neural networks can do really well in what's it called? Like taking that complex information and designing it. It turns out to the reason why we can do this, like why neural networks are a big deal, is that we just have a lot of data and we have a lot of computation power. So this actually, interestingly enough, is that the idea of neural networks actually was developed back in the 1950s. And like there's a paper about it and they kind of go through and also about perceptrons and neural networks. But the real thing is that we couldn't use any, like, it wasn't very useful by itself because you had to have a lot of data. Basically, you had to have a lot of examples of saying inputs and outputs. And then you also had to have enough computational power. So essentially, like, if you didn't have a lot of data and you didn't have computational power, which 1950s, I don't know if you guys know about computers back in 1950s, weren't that great back then. In fact, a big resurgent, like, I don't know if resurgence is the right word, but like a real reason why neural networks are such a big deal right now is that we have parallel processing units. Usually, for example, GPUs have been the most recent thing. The funny thing is that GPUs were designed not in neural networks in mind. They were designed, if you guys are, doing any gaming on a computer, they're mostly doing for gaming, for graphics, but it turns out those were optimized for parallel processing. So if you think of like a CPU, a GPU is a graphics processing unit. That is one of the reasons why neural networks work really well. Is neural networks work really, really well when you can parallelize it. In fact, now there are even newer things called TPUs, tensor processing units, that are basically designed just for artificial neural networks and stuff like that. So that's kind of like the reason like what this motivation comes from. But I want to emphasize that even though like neural networks are pretty cool and like they're super hot right now and everything like that, and I'm pretty sure that they will be becoming more and more important in machine learning and data science in general, they're not always the best tool. So you have to always keep that in mind. Okay. So now that I've talked about like this, like a neural network and everything, let's talk about like the first part of the neural network, which is a perceptron. So this is basically a perceptron. I think this actually might be directly from the curriculum. I can't remember where I borrowed this from. But the idea here is that we have our inputs, which you can see is X1, X2, X3. We combine them together into a single node right here. So if you kind of think back in graph theory from that section 42, I think, is that these are kind of like essentially a graph, but you don't really need to know graph theory to understand neural networks. But the idea here is we take X1, X2, X3, and then these arrows are representing saying we do something, we basically multiply it by some number, and we combine them together by just essentially adding them up into this node. So if you imagine like X1 is 1, X2 is 3, X3 is 2, that's really confusing. I'll just say 1, 2, and 3. And then we just multiply, you say, okay, X1 by 1, X2 by like 0.5, and X3 by like 2. We would have a 1 here, and then 6 here, add them up together, that would be 8. So this total inside would be 8. And then usually what happens in this point, we have another function, what we'll call an activation function. We'll go into more detail. But this activation function then takes that value in there and transforms it in a nonlinear way, and that will be our output. But in general, that's the idea here. Is we take these inputs, we multiply them some numbers, we add them together. We might do another kind of function, another mapping essentially of that number, and then spit it out as an output. And that's really what a perceptron is. So if you think about this, this is really close to a linear regression. So you remember at linear regression, we basically just had a, x1, which is like, your column, right, times some value. Note that I'll put W1 for weight and stuff like that. That's pretty common. And basically just add up those parts in there together, and that will give us an output. So that's more or less really what a perceptron is doing. And it turns out, like if you look at it like this, you're like, hey, we know linear regression. Linear regression was easy. That was like back in Mod 1, right? So this isn't like too crazy. And what's going to be the real power about this, it's not going to be a single perceptron, but basically using perceptrons and putting them together to make more complicated systems. And that's really where the real magic goes. Note that I put originally right here, X1, W1, X2, W2. You can also write this as matrices. So if you see, for example, capital letters in mathematics like this, usually in context, that means matrices. So you can imagine X is going to be a column of X1, X2, X3. And W here basically is same thing as a matrix of weights. Okay, cool. All right, any questions on this general thing? No? Sound pretty good? Okay, so now we can just see like, okay, how do we do some, little logic and stuff like this? So a perceptron is actually still pretty powerful even without making it too complicated. And it allows us to basically separate out data. So think classification. So one classic one that you can talk about for perceptrons is doing something like logical OR and logical AND. So is anyone familiar with like logical OR, logical AND? Just kind of give me a thumbs up if you are. Thumbs down if you're like, I don't know what that is, because we'll talk about it. Okay, we'll see some thumbs up, see maybe some questions like, maybe not, right? So we'll talk a little bit more about how that goes through. But anyway, this is a little function. We'll kind of go through a little bit. But basically, this is going to build up this W1 or X1 W1 plus X2 W2 without the X3 here. And we're going to combine them together. Just note that we'll kind of walk through this in a second. So just ignore it for now. All right. So the actual problem. So let's say we have this right here is logical, like a logical notation right here, is A and B equals C. So the idea here is that A and B can either be true or false, or 0 and 1. So 1 being true, 0 being false. And this right here is usually what we call a truth table. And so basically the idea here is that combining these together, we'd get a value C. So for example, if A and B are 1 or A and B are both true, then C is true. But if A is true and B is not true, then it means C will not be true. So, or we represent that as 1 and 0 gives us just 0, okay? And you can see it's symmetric, so 0 and 1 will also give us 0. And then of course, if neither are true, they're both false, both 0, they're gonna give us 0. So this is basically a list of inputs, A and B, and a list of outputs, C, right? And this is where basically we can kind of figure out like, okay, like how do we design our perceptron to make this work? And so our perceptron, and this is where I didn't have my nice little diagram here, I just kind of wrote this out in little text code right here. It's just basically our first value, x1, x2, b, which note that this b here stands for bias. Usually we tend to have a bias in there to allow us to have a little extra, basically push up and push down. So it kind of helps us without having to incorporate this into W1, W2. And then this x1 times W1 will be a value, x2 times W2 will be a value, and then b, which usually we classically just have it multiplied by 1. So sometimes you'll just see this labeled as just b. And those will be put together and then combined into a linear combination. And then what we say, if we just want to say, is it 1, true or false, we basically can say, okay, is it greater than or equal to 0? So this is kind of like that little part where I said, where you get the node here, and you say, okay, you get all the linear combination, and you do some kind of transformation on it. And that transformation is going to be something along the lines of like transforming into something nonlinear. So note that greater than or equal to 0, it's not really linear in that way. It's what we call a step function. Okay. So this is how we're going to build up our perceptron network. We're going to build up our little perceptron and see if we can figure out the ways to modify W1, W2, and then B, what values we need to put in there to actually, when we put in 0 and 0 for x1, x2, we'll get 0 for C. But if we get 1 and 0 for x1, x2, we should get 1 for C. Okay. Does that make sense to everyone? Okay. Any questions on clarifying this part? So note that I could have just used this guy right here and just changed this to B, and that would be pretty much the same diagram as I'm trying to write here. Okay, so, all right, so this is where I kind of go a little bit of like how this works. So we have our test inputs and we have our our correct outputs. So note that basically this is going to represent x1, x2, right, or A and B, and this should give us false. And 0 and 1 should give us false, 1 and 0 should give us false, and 1 and 1 should give us true. Did I do this right? Yes, okay. Just want to make sure I wrote that right. But we're going to take these parts and we're going to feed this into our logic part after we define what W1, W2, and bias are. So just kind of showing you a little bit, very briefly. It's not important for you to like understand this full code to like understand this problem. But the idea here is going to take our inputs and then our correct outputs. And it's going to create our linear combination. And then going to say, okay, is it 0 and 1, basically, like doing that transformation. And then we're going to compare our, what's it called, our correct outputs with our outputs. So that's what this part will be here. And this will give us a little output. So just to kind of show you a little bit what this looks like versus like, just me showing it to you, is that let's say we just set our values to 0, 0, and 0. Really unexciting kind of stuff, right? So I got to run this guy and I test it out. So we're going to see if it actually makes the correction, or the correct prediction. And you can see here input 1 and input 2. So this is like x1, x2. You can see x1 for 0, x2 for 0. And our linear combination, well, we're just going to add these together with no weight, right? The weights for 0, 0, so it's just going to be 0. And then saying, okay, is this 0 greater than or equal to 0? Yes, it is greater than or equal to 0. So we have an activation of 1. But is this the correct thing? No, it really should be, in this case, 0, 0 should be just 0. So you can see it's not correct, right? And by chance, we just got this very last one correct. Okay, does everyone make sense? Or does everyone understand how this connects with the truth table? Yeah, any questions so far? Feel free if like if something doesn't seem quite right. Okay, so I'm gonna ask you guys, what do you guys think, any ideas of what we should put these W1, W2 bias? And feel free to randomly choose too if you're just like, I'm not sure. And note that you can do positive numbers and negative numbers.
Are we supposed to come up with like specific numbers or just anything?
Yeah, I mean, you can think, if you can think of it strategically. Remember, this is going to be like x1, so like whatever x1 is, which is either going to be 0 or 1, times w1, x2 times w2, and then b, and then you combine those all together, sum them together, and see if that's greater than 0.
Maybe like 2 and I don't know.
Let's try 2, right?
3 or something.
2 and 3?
Yeah.
Okay, worth a shot, right? And okay, so we didn't get anything here, but you can see the linear combination, 0 and 0, 2 and 2, 2 and 2, and 4. So this was going good, right? So this is looking pretty good. But this one, we need to have these output as 0, right? So when, let's say start off with this input is 0, output is 0. Or sorry, input 1 is 0, input 2 is 0, right? No matter what we multiply it, it's going to be 0, right? So what's the only part in here that we could change that could modify this line in this case?
Bias.
Bias. All right, cool. I heard bias. So good, right? And we need this line right here, since it's 0, 0. We need this to be less than 0, this linear combination, right? Because we want this to be false, right? So what could we put for bias that would make this combination less than 0? I'm sorry.
A negative number?
Yeah, negative number, right? So -1. Ones are nice. Okay. So let's just try that. I'll keep these at 0, right? And then we try this guy out. And you can see, okay, looks like we got the, hey, look at that. Just changing -1 here. We got everything else correct. Awesome, right? But now you can see we don't have this one because 1 times 0 plus 1 times 0 is 0, right? And then -1 is like, it isn't quite right. So anyone got an idea of what maybe we can change W1, W2 to? Maybe make this guy work.
Sorry, Victor, do you mind explaining the activation output again?
Yeah, so all it's going to happen here, so if I wrote this out like here, it's going to be x1 times w1 plus, oops, and then let's see, x2, oops, times w2. Gosh, why can't I can't talk anymore. And then plus the bias, right, which is multiplied by 1. And then what's going to happen is say, okay, this is going to be some linear combination, right? And then what we're going to do is say, is this linear combination greater than or equal to 0? And so this is going to say either true or false. That's what that activation is going to be. Yes, or true
Gotcha.
for 1, 0 for false. Does that make sense to everyone?
Okay, thank you.
No problem. Okay. So right now we have a -1 here, right? And we want this to be at least 0, right? In order for this to be true, because we want this activation to be 1, meaning true. How could we counteract this by, we'll assume bias is just -1. And then if you think of a specific scenario. I hear someone. Can't quite hear you though.
0, 1, 0.
1, sorry, 0, 1, 0?
No, 1, 0, -1.
So 1, 0, -1, like this?
Mm-hmm.
Okay, so let's try that out. And hey, okay, we got it right, but you can see here, okay, not quite right. Anyone got another, like, it looks like we did this right, but it looks like this isn't quite when it's either or, because we want these to be 0 as well. Anyone got one last guess of what we can change W1, W2 to be?
Change them both to 0.5.
All right, let's try that. And there we go. All right, so you can kind of see a little bit like the structure now has it where we can always get these correct answers. And I think if I wrote my solution here, That's what I wrote down too. So you can kind of see how you can form this in a little bit. And now what happened is that by setting these weights W1, W2 and bias, you now have a perceptron that if you feed in just zeros and ones, it will basically tell you, is it it's a, what's it called? A logical and, right? So if x1 and x2, and it's going to give you an output of that's true or false. So if you're big into computer science, that's actually a really big deal because you're going to have all these different logical and gates and stuff like this. And I won't go drive the next one, which is going to be logical OR. So we could do the same thing, trying to figure out, what's the best way to do this, right? In this case, logical OR, if at least one of them is true, then the whole thing is true. So you can see basically the only time it's false is going to be 1, 0, 0. Okay. So if you were to actually figure this part out, if we just do the 0, 0s, you can see not quite, right? But if we do the solution here, we can actually set weights to 1, 1, and -1, and then we should get all correct. So this is kind of showing you a little bit like how the structure and like if you notice this, the structure should be the same, W1, W2, and the bias. Both of those look exactly like this. And all we have to do was just change the weights of basically how they're being multiplied. And this will actually change the structure, or not the structure, but like the function of what's going to happen. So that's the idea of these perceptrons. Okay. So I thought that was an interesting example. This is a classic one that you might find. And there's also another one like an and or not and, so a NAND, N-A-N-D gate, but I won't go into that one because that's a little more complicated. But yeah. Okay. Any questions on like how this all kind of forms together to make, an output? Okay. Sound pretty good? Okay. So that's our little perceptron. And you're like, okay, that was fun, Victor, but let's see some really interesting stuff. Like we're not going to do a bunch of zeros and ones, right? Just for these little perceptrons.